Hello, welcome everybody. I am Surendra Jain, Master Teacher of Mathematics in Vedantu. In my weekly sessions on CMI and ISI preparation, I am solving for past few years only previous year papers like CMI and ISI. So this week also I am taking CMI 2022 Part B that was conducted on 22nd May. Last week I took part A and I think that was an easy paper, but this part B is not that easy. In fact, you can consider this as a difficult paper also. And here all CMI conducted two papers this year. One was 22nd, one is 23rd May. So coming weeks I'll be taking up other papers as well. So let us start solving this year paper. So we have a question in which triangle X, Y, Z, the following constructions are made. Mark point W on segment XZ, point P on XW and Q on YZ, such that this WZ upon YX and similarly PW upon XP and QZ upon YQ, they all are equal to K. Use the schematic figure not to scale, extend XP, QP and YX to meet at the point R as shown, and we have to prove that this XR is equal to R, XR is equal to XP. This is what we need to prove. Okay. So dear all, what I am going to do, first of all, as per the convention of any triangle, let us take side opposite to capital Z vertex as small z. Similarly, small y opposite to y and so on. Now, as per these ratios, we are given that this YZ length is equal to K times Z. YZ upon YX is equal to K, so this is K times Z. Then PW upon XP is equal to K. So if we take this as T, this will become K times T here. And here you can check that this side XZ, which is actually opposite to capital Y, is actually the sum of three things: T, KT and KZ. Okay, and third ratio is QZ upon YQ. So this ratio is K ratio 1 here. Okay, now to prove this I have two methods. One is using vectors and one is using geometry. So first of all, to do this by vectors, I will assume this X to be origin. So its position vector will be O. And let us assume this X, Y, let us assume a unit vector A cap along this side XY and unit vector B cap along XZ. Then we will be able to write this point Y as Z into A cap and this Z as Y into B cap, where Y is this T plus KT plus KZ. And also this Q point, which is dividing YZ in the ratio 1 is to K, its position vector will be 1 into YB cap plus K into ZA cap upon 1 plus K. So that will be the position vector of Q. Now position vector of P can also be written because it lies on XZ side, along which unit vector is B cap. So we can write this as T into B cap. Now we have to prove that XR is equal to XP. So let us take this length as R. So we will be proving R is equal to T. Now this XR is opposite to XY direction and this length is R. So this position vector of R will become minus R into A cap because it is in opposite direction, that is a minus. R is just the length. Okay. Now we are given that this R lies on the line joining PQ. That means this RP vector should be lambda times, that is scalar times some vector PQ. And here we can write this as OP minus OR is equal to lambda times OQ minus OP. So let us put these position vectors one by one. OP is TB cap, OR is minus A, minus R A cap, so minus minus plus R into A cap is equal to lambda times OQ, which is YB cap plus KZ A cap upon 1 plus K minus OP, and OP here is TB cap. Now because A and B are two vectors which are not collinear, So if this equation is to be true, coefficients of a cap and b cap, they should be compared separately. They should be equal separately. Then only this equation can be hold good. Now coefficient of b, if you compare, it comes out to be t on the left hand side. On the right hand side, it will be lambda common and y upon 1 plus k, y upon 1 plus k minus t. Okay, and if I write the value of y from the equation number 1, we get t plus kt plus kz upon 1 plus k and minus t here. So if I take LCM, this 1 plus k, so t into kt. So these two terms you can check, they will get cancelled. So what we will be getting is t as lambda into kz upon 1 plus k. So that is the value of t that we are getting. Now comparing the coefficient of a cap, my left hand side is r, whereas right hand side is lambda into kz upon 1 plus k. And you can check this t and this r, they both are same thing. So t is equal to r, and that is what we need to prove, that is xr is equal to xp. So this completes the solution of this question with vector method. I think this vector method works most of the time. Sometimes you find calculation to be difficult, but what you should do, you should choose your origin so that calculation becomes easier. Here, if x is at origin here, and I have chosen x because most of the point you can check p, r, y, z, w, except q. You can check all the points are such that they are lying on some line which is originating from x. So x was the right choice to do this question by vector method, and calculation will be least. Now coming to second method of this question, that is using geometry. So what I have done, first of all, I will use same convention as I did in previous method. I will take x, y as z. I will take this xp length as t, okay, and then pw will become k into t, okay. This wz length would be k into z. So all these things are same, okay. But what I have done here, I have done one construction extra, that is I have drawn a line that is parallel to yx passing through q, which meet this xz at the point s here. Okay, these two diagrams are same except for the fact that here s lies between w and z, and here this s is between p and w, that is beyond w and z. But calculation is going to be same. There is going to be no difference at all. Let us see this one by one. Okay, so first please see, because this qs is parallel to yxr, so this point, this angle at r here will be equal to this point at q here, that is alternate angle. And here angle at p point in this this triangle above and this triangle below, they will also be same, and hence third angle will automatically be same. So we can say these two triangles, that is RPX is similar to triangle QPS. Okay, now if we need to prove that this XR is equal to this XP, so what we just need to prove that these two angles will be same. So if we are able to prove that these two angles are same in both the triangles or any one of the triangles, then our job is done. Okay, so our objective here would be to prove that these two angles are same, or in the triangle which we have formed with the help of this S point, if we can prove that PS is equal to QS, then also our job is done. So that is our motive here, because if PS is equal to QS, then by symmetry or by angle, both of them you can say XR will be equal to XP. Now, because QS is parallel to this, QS is parallel to YX, and this YQ upon QZ is equal to 1 upon K. As you know, this is also given to us K ratio 1 ratio. So from this we can conclude this length QS going to be using BPT, basic proportionality theorem, K upon K plus 1 into this YX. because y-axis is parallel to qs, so the ratio will be k upon k plus 1 into z. So this is what qs we have obtained. Now after this, I will do the calculation that will be applicable to both the diagrams. Please see how. In fact, so far also we have done same calculation. So now my objective is that to prove PS will be same thing here as well. So PS, if you check, it is actually PZ minus SZ. And in this diagram also, PS is equal to PZ minus SZ. So it is actually true for both of them. Not only this, this also. Now what is my PZ? Now to do this thing, please understand here also this length y, as I did in our previous method also, this y length is equal to T plus KT plus I think KZ. Okay, and here PZ, if you see, it is PW, that is KT, and WZ, that is KZ. And SZ also using the same BPT theorem in that same triangle here. This will also be, let me write it here, it will be K into Y upon K plus 1. SZ and QS, they are corresponding sides to that triangle XZ and XY sides. In that bigger triangle XYZ, and if you compare this SQZ, so this QS and SZ are corresponding sides to YX and XZ. So SZ is KY upon K plus 1 and QS is K upon K plus 1 into Z. Now this SZ I can write as KY upon K plus 1, and this SZ is equal to KY upon K plus 1 is valid here as well. You can check. Now what we can do, we can put this y value in this ky upon k plus 1. So what we will be getting, kt plus kz minus k common, and y is t plus kt minus kz upon k plus 1. In fact, you can check k is coming common everywhere, and if we take k plus 1 LCM, okay, so that will be t into k plus 1 plus z into k plus 1 minus t minus kt and minus minus plus kz. So let us see what all terms will be cancelled. I think this kt is getting cancelled, this t is getting cancelled, okay, and I think that is all. That is what we are cancelling. Just 1 minute. I think here also it is plus. Yeah, for y it is plus here, so this here will also be minus here. So this kz is also cancelled. So what is left? I think only z is left inside this bracket. So kz upon k plus 1. So you can check that ps is coming out to be sz, is coming out to be qs, is coming out to be qs. And from this, using similarity or whatever you say, you can say this xr will be equal to xp, and that is how this is done using this BPT or geometry, you can say. Okay, now coming to second question, but I think this question was a good question, and if you have patience and you can do any one of these, either this or vector. Actually in vector you don't have to think about of any construction. All these result that comes because of construction, they will come automatically, that if you use your origin suitably and you mark all these position vectors. So I think this one I will say was easier, but if you are good at geometry, then this is also good. Okay, now coming to next question, which says in xy plane draw horizontal and vertical lines through each integer on both axes so as to get a grid of small 1 into 1 squares whose vertices have integer coordinates, okay, like 0, 1, 1, 3 and so on. Consider a line segment D joining 0, 0 with m, n. Find the number of small 1 into 1 squares that D cuts through, that is squares whose interiors D intersect. Interior consists of points for which both coordinates are non-integers. For example, line segments joining 0, 0 and 2, 3 cuts through 4 small squares that can be checked using drawing. So let us try to see what will be the number for any general m, n. To understand that, what I have done, I have drawn a grid, and it is a 12 into 12 grid, you can check, and I have taken 2 points. One point here is 5, 7. You can count 1, 2, 3, 4, 5 on x-axis, 1, 2, 3, 4, 5, 6, 7 at y-axis. So this is 5, 7. Now this is my O point, or rather they have called this as D point. Let me call also this as D, and this point as A. So what you can check, the slope of this DA is actually 7 upon 5, and 7 and 5 are co-prime. That means this fraction 7 upon 5 cannot be simplified further. If you try to write this in the form of P upon Q, where P and Q are integers, then 7 and 5 are the smallest possible integers to write such thing. Smallest possible positive integers to write such things. What does that mean? Because of that, I will be able to claim that this straight line is never going to meet at any such junction. Like A is a junction where horizontal and vertical lines are crossing. This line DA will never be able to meet any such junction, and you can see it from diagram also. Every time this line is either meeting horizontal line or vertical line, but not both of them together at one point. And why it is so? Please listen carefully. Suppose there was a point B between D and A where this line will meet, and which is the junction of horizontal and vertical line. Then because B will be lying in between, okay, so if B is between D and A, then slope of DB will be equal to slope of DA. And because B is between D and A, and if B is a junction point, then this slope should also be some P upon Q form. But as I have told you, it is not possible to have this this simplification of 7 by 5 to some smaller integer. So this point B can never be obtained between D to A. So the conclusion is that whenever you have m, n, where m and n are co-prime, okay, so we can say that between D to A, we will never be able to get this line cutting horizontal and vertical lines together, that is passing through a junction point. Now, if this line is not passing through junction, what does that mean? This means that between this D to A, if suppose this point is M, okay, then this line D to A will be meeting M minus 1 vertical lines. You can check through this also, like for this D to A, first vertical line it is meeting here, second vertical line, third vertical line, and fourth vertical line. So between D to A, it is meeting 4, and here it will be M minus vertical line, and similar to this N minus 1 horizontal lines it will be meeting when passing through D to A. And you can check these are the horizontal points 1, 2, 3 and 4, 5 and 6. So 7 was the y coordinate. So horizontal lines it will be meeting 6 times for D to A, and in general it will be n minus 1. Okay, so you can check. So point of intersections are m plus n minus 2 in number. Okay, and what you can see, every time whenever it is meeting either horizontal line or vertical line, and they are never together. So whenever it is meeting horizontal line, it is actually crossing one of the box of 1 into 1 size to another box of 1 into 1 size. Same is the case when it is meeting a vertical line, then also this line is crossing one into 1 box to another 1 into 1 box. So here you can check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 boxes that it is intersecting. Let me just check once again. 1, 2, 3, 4, 5, 6, then this 7, 8, 9, 10, 11. Yeah, it should have been actually 11. Yes, so there will be 11 such boxes through which this line will be crossing. Okay, and that is what we are looking for. Let us read the question once again. Find the number of small 1 into 1 squares that D cuts through. So D is actually cutting through 11 boxes in this case, and this is actually one more than the number of point of intersection. Why it is so? Because even before, when it intersected first horizontal line or any first vertical line, it was passing through this box here. So this box is coming even before first intersection of this line DA with any of the horizontal or vertical line. So in case of m comma n, here this number of boxes that it will be intersecting boxes would be this. Just add one more here. So m plus n minus 1 will be the answer if m and n are co-prime. Now, if m and n are not co-prime, I have taken this example. Please see, this point is 9 comma, this is 12 comma 9 actually. This point I have taken as 12 comma 9, and they are not co-prime. So you can check this line is meeting at this point, and here also you can check this y coordinate is 3, x coordinate is 4. So this point is also, you can check 4 comma 3, which is having same ratio between x and y coordinate which 12 comma 9 is having. And once again it is meeting here. There also it is 8 comma 6, and again the ratio is same, 8 comma 8 is to 6, 12 comma 9, or 12 is to 9, or 4 is to 3, they all are same. So what does that mean? That if m comma n, m and n not co-prime, and let their GCD m comma n, their GCD is equal to, let us say, D. Okay, then I can write m as m naught into D and n as n naught into D, and then m naught and n naught will become co-prime. Okay, and as I shown you, for 0, 0 to 12 comma 9, there were 3 portions. 4 and 3 are co-primes. So 0, 0 to 4 comma 3, and you can use this theory which I used here. There will be 4 plus 3, 7 minus 1, 6 boxes. This line will be intersecting between 0, 0 to 4 comma 3. You can count it. And same 6 will be between 4 comma 3 to 8 comma 6. And then same will be 6 between 8 comma 6 to 12 comma 9. So if D is the GCD, here this GCD was 3. So D times, you will be able to see that same pattern being repeated. Okay, so what we can say, let me do it here. When m comma, this is another question. So let me use it here. When m comma n are not co-prime, okay, and then let us say m is equal to D times m naught, n is equal to D times n naught, then this answer will be D times m naught plus n naught minus 1, with the same logic which I told you here. Because if m naught n naught are co-prime, then the number of boxes this line will be intersecting is this thing, and it will be happening D times. So D into m naught will be, I think, m, D into n naught will be n minus D. That is the answer for this first part. Okay, for first part there are two answers. One is this m plus n minus 1, and another one is this. Okay, now coming to the second part. The second part says, now L is allowed to be an arbitrary line in the plane. Find maximum number of small 1 into 1 squares in n into n grid that L can cut through. That is, we want L to intersect the interior of maximum possible number of small squares inside the squares with vertices 0, 0, n0 and 0 n. So you can assume this to also be like 0 comma n here, and I have taken here as 12. So this point to be 0 comma n, this point to be n comma 0. Okay, so which line will be there in which we can have maximum intersection with these 1 into 1 squares. So first of all, this maximum number of intersection will be when you are intersecting maximum number of vertical lines and maximum number of horizontal lines. I hope that is clear. So in order to have maximum number of intersection, my starting point should be, because L is an arbitrary line, this time they are not saying that it should pass through 0 comma 0. So here this line should be lying somewhere here. This line should start from some point here and it should go some point here, so that we will be having all horizontal line being intersected and we will be having all vertical line being intersected. Okay, but there are chances that if we choose such points randomly and joining these lines may pass through some of the junction point, that will reduce our number of boxes being intersected. So better would be that I start with this D. Let me make this diagram first. Let me use this diagram once again. Yeah. So what I was saying, that in this case I was suggesting that we should have last point somewhere here and initial point somewhere here. But to make sure that we will be having all intersection with the horizontal line and vertical lines separately, what we can do, we can start with this point. This will also make sure that all horizontal lines are being cut and all vertical lines are also cut. And we take this point to be here if this point, if this m comma n are co-prime, but because this time they are saying this is n comma n, so obviously they cannot be co-prime. So if you join this point with this, you will find this line will be passing through all these junction point. In fact, there will be least possible intersection of this line with these boxes. So what we should do, we may do one thing, we can take a point maybe here, or we may take point somewhere here. So if we join this point with this origin here, okay, and such that this point here, you can call this as n minus 1, you can call this point as n. So between these two, if I take this point as x, let us say, and x is this x is a irrational number between n minus 1 and n. Why I am taking irrational number? Because if this is irrational, okay, and this point will be actually x comma n. So the slope thing here would be y coordinate is n and x coordinate is x. Okay, so this will be irrational, and if it is irrational, then this line which is starting with 0 comma 0 will never be able to meet any of the junction point. So it has to cut either vertical line only or the horizontal line only. So if I start with 0 comma 0 and I join with some x that is irrational between n minus 1 and n, this x could have been here also between this n and this n minus 1 also. Then also you will check this slope will be irrational and this line will never be able to meet the junction point and our intersection will be maximum. Okay, so if we join 0 comma 0 to this x comma n or n comma x, in both cases you can see number of intersections would be, I think, n plus n minus 1, that is 2n minus 1, and that will be the answer of this question. Okay, because this is going to cut n horizontal line and vertical lines. Okay, going to cut n minus 1 horizontal line, n minus 1 vertical lines, and plus 1 because in the beginning itself we were having intersection with one of the box, or you can say this line was passing through one of the box. Okay, what they were saying, cutting through means I have used the word intersection, they have used cutting through, and they have explained what is the meaning of cutting through. Okay, so this completes the this question. Let me write the answers of all the parts separately. M plus n minus 1 is 1. M plus n minus d is other answer of first part, and for the third part, second part, it is 2n minus 1. So these are the answer. This was, I will say again, a good question. I think this question is something that you might have seen in some previous year Olympiad also. So this concept could be old concept to familiar concept with some of you. So for those students, this question could be easier, but not easy for those who are going to do this question for the first time. Now coming to the next question. Here we are given for a positive integer n, fx is equal to 1 plus x power 2 and so on. Find number of local maxima of fx. Find number of local minima of fx for each maximum minimum c comma fc. Okay, so c will be point of maxima or minima and fc will be the corresponding value of function at that c. Find the integer k such that c lies between those two integers k and k plus 1. They have given hints, and as I was saying in the beginning, paper was difficult and they have given you hints also so that you can understand the hint and you can, probably your chances will become better to solve this question. So it may be helpful that look for small n, maybe you can start with x is equal to 1, 2 and so on. Use definition of f as well as a closed formula and treat x greater than 0 and x less than 0 separately. Now to do this question, what I am going to do, I will be first doing this question by doing the differentiation of this fx, which becomes here 1 plus 2x plus 3x square and so on, plus n into x power n minus 1. So as they said, treat x greater than 0 and x less than 0 separately. So this f dash is going to be positive for all x that is greater than or equal to 0. So that means there is no chance that this may have maxima or minima when x is positive. Okay, so for x positive, no point of either maxima or minima. Now coming for x less than 0. For x less than 0. So first of all, what I will do, I will write this fx to be x power n plus 1 minus 1 upon x minus 1, which is valid whenever x is not equal to 1. And when we are talking about x less than 0, so this cannot be equal to 1. Now, let us do the differentiation here. So f dash x here would be quotient rule of differentiation, n plus 1 into x power n into x minus 1 minus 1 into x power n plus 1 minus 1 whole divided by x minus 1 whole square. Okay, now let us simplify it. So here x power n plus 1 we are getting here, and also we will be getting x power n plus 1 with the coefficient n plus 1 here. So simplifying it will give us n into x power n plus 1, and then x power n term is also there with minus n plus 1 into x power n here, and then constant term is I think plus 1 here, whole divided by x minus 1 whole square. Now we are focusing on x less than 0 for x negative. Now again, n here is some positive integer, so n could be even also, n could be odd also. So if you take n odd, you can see n plus 1 will be even. If n is odd, n plus 1 would be even. And if that is so, then this first term here will be positive, but x power n will be negative. For x negative we are talking about, so you can check f dash x here also comes out to be positive only, because this is positive, this minus sign and this negative thing will be make it positive, so this will be positive only. So again we can say that for n odd, no point of maxima or minima. Now coming to when x is negative and n is even, I think that is the only thing that is left now. And f dash x, if you remember, it was n into x power n plus 1 minus n plus 1 into x power n plus 1 upon 1 upon, I think, x minus 1 whole square. Now if n is even, n plus 1 will be odd. So this term here would be negative and this will be positive, but with minus sign this will also be negative. So it looks like f dash x going to be negative this time, at least for 1 point, and let us see whether it will be 1 point or some more points. So I'll call this gx, that is written in the denominator. So gx is actually here n into x power n plus 1 minus n plus 1 into x power n plus 1. Okay, now whenever g will be negative, f dash will be negative, g will be positive, f dash will be positive. So let us see what is the behavior of gx. Here you can check g0 is definitely positive, that is 1. And if I put some negative value of x, let us say if I put g of minus 1, okay, so it will be because n is even, so that will be minus n here, minus n minus 1, okay, plus 1. So you can check this comes out to be negative. So what we can see that this gx will be positive at 0, negative at minus 1, but whether there are some more possibility where this gx can change its sign, and there this f dash will also change its sign, and there we may find some point of maxima or minima. Okay, now to do that, let us check the monotonicity of this gx function. If I differentiate this function gx, we get n into n plus 1 into x power n minus n into n plus 1 into x power n minus 1. So if you take n into n plus 1 common and also x power n minus 1 common, we get x minus 1 here. And what you can see, n is even, so n minus 1 will be odd here. Okay, so you can check there are two critical points, 1 and 0 for this g dash x. So it will be positive here, it will be negative here, and power on x is because odd, so here also there will be change of sign. So what we can see, this g dash function is going to be increasing for all x that is from minus infinity to 0. It will be decreasing for all x that are from 0 to 1, and again it will be increasing for those x which are from 1 to infinity. So here you can check, because g function is, value of g function is 1 at 0, okay, and minus 1, yeah, minus 1 will be here, and at minus 1 it is negative like here, but from minus infinity to 0 it is strictly increasing, so this graph will be like this, and after 0 it is decreasing, it will be decreasing. But if we check the value of g1 here, okay, in fact we are supposed to check only for x negative, so let us not do for anything that is where x is positive. So what we can see, between minus infinity to 0, that is when x is negative, this gx can be 0 only at 1 point. Only at 1 point gx becomes equal to 0. This is the graph of y is equal to gx for x negative. For x negative. Okay, and you can see about this point gx, sign is actually negative to positive. So here also for f dash x, let us call this point as c, as they have also used c in their question. So at c point you can check this f dash will become 0, but about this c, the sign convention will be like this, negative to positive. So you can see this c point will be a point of minima, point of minima. Okay, so let us read this question once again. For maximum minimum, for each maximum minimum C, there is only one point of minimum that we have found, and we have to find integer k such that C lies between these two integers. So here it is very much clear that this C lies between -1 and 0. Okay, so let me write the answer here. What they are saying, find the number of local minima. Local minima, number of local minima is equal to 1. Okay, find number of local maxima also. Find number of local maxima is, I think, 0. And for each minima, not maxima, because there is no maxima, C lies between k to k plus 1, and this k is actually equal to -1. You can check. So these are the complete answers for this particular question. In fact, they have said you can start with taking a smaller value of n. So let me show you if you could have done that also. This will give you idea that suppose you take n is equal to 1. Okay. Suppose we take n is equal to 1. Then this function will be fx is equal to 1 plus x, which is strictly increasing. For n is equal to 2, fx is equal to quadratic, 1 plus x square, and this is supposed to have a point of minimum. And you can check this is at -1/2, which is also between 0 and -1 at n is equal to 2. If you take n is equal to 3, then fx will be 1 plus x square plus x cube, and its derivative, if you check, I think this gives you 1 plus 2x plus 3x square, and whose d is negative. And if d is negative, that means f dash will be always positive. That means fx will be strictly increasing. So what we are getting for these values, that for n odd, this comes out to be strictly increasing. And for n even also, this function is having one point of minima, and that is when x is negative. And this thing we have done properly for any n. So this, I think, complete this question. Again, I will call this to be a good question, not easy question. Average or average plus it should be counted. Now coming to next question, it says that r plus denote the set of positive real numbers for a continuous function f. R plus 2r plus define AR equal to area bounded by the graph of f, x-axis x is equal to 1 and x is equal to r. BR is the area bounded by the graph of f, x-axis x is equal to r and x is equal to r square. Find all continuous function f from r plus to r plus for which AR is equal to BR for every positive integer. So let us do it. They have given some hint also. I'll use that also, but let me tell you my first method here. We are given that 1 to r fx dx is equal to r into r to r square fx dx. Dear all, let me tell you, this integration will denote area only if r is greater than 1. Okay, otherwise if r is less than 1, please listen carefully, AR is equal to 1 plus r fx dx, because area has to be positive. This will be if r is greater than 1. If r is negative, r is less than 1, r is between 0 and 1, then this limit is actually in reverse order. Then this integration will give us negative. So to write correct area, I think we should be using minus sign outside with the same integration if r is between 1 and 0. But if r is less than 1, r will be bigger than r square. So both time if they are positive, so this will be positive, this will also be positive. If this is negative, other will also be negative. So in both cases, whether AR or BR, they both will be given by this 1 to r or r to r square or negative of this. So in both scenarios, if AR is equal to BR, these two integrations are going to be same. Okay, now my first method is that I am going to put this x is equal to some u into r. If I do that, this r limit will become 1 and this limit will become r. And here we will be getting f of ur and dx will become r into du. putting this u back to x, and by changing the name of integration variable, integration will not change. So it is xr into r into dx. Now please listen carefully. 1 to r fx and 1 to r f of xr into r, their integrations are same, and that too for all r that is positive. Okay, that means, please try to understand, that means these two fx and f of x r into r, they should be same. Why I am saying so, please try to understand. Suppose we started with 1 and we went to some value of r, and both of them were giving you same area. Maybe this one, first one was giving you because its shape was like this, and other one was giving you because its shape was like this. So these two area can be same. But first of all, if your shapes of these two graphs are two different curves, then if I bring this r here, you can check their integrations will not be same. Okay, but suppose for some r these integrations become same, and now I increase r by some small value, and it goes like this, it goes like this. So suppose if this up to this point their integrations were same, then after that they will not be same, because one function is going like this, one function is going like this. So this elementary, or I should say differential, actually not elementary, differential area that is being added when I change my r to, let us say, r plus delta r, these two will not become same. So these two become same for all r that belongs to r plus only if this fx is equal to f of xr into r. Now I'll be multiplying both sides by x, and you can check this x into fx is actually becoming rx into f of xr. If you take rx as y, this is actually becoming y into fy. Now r is any positive integer, because they are saying for every positive number. So irrespective of what x was, I can choose any r. That means for every value of y and x, this x into fx and y into fy should be same. So if that is so, this is for all r and all x. So this will be true only if they both are some constant value, let us say k. So if that is constant, then fx will be equal to k upon x. So that is the answer of this question, that fx can be any function of the form k upon x, where k belongs to r positive, because function is positive, so k also has to be r positive only. So that is one method. I'll tell you one more method. Actually, they have given some hint that we should use some method of convergence and all. So let me tell you what exactly they are talking about. Method 2. 1 to r fx dx is equal to r to r square fx dx. So if I do the differentiation both sides, I will get, and differentiation is with respect to r. So differentiation of r is 1, and then we will be putting r in place of x. Differentiation of 1 is 0, so there is no need to write corresponding to lower limit. Then 2r into fr square minus 1 into fr. This is actually use of Newton-Leibniz formula. So we get 2 times fr is equal to 2r into fr square. So here this 2 gets cancelled, and we are getting, if I multiply both sides by r, so r into fr is equal to r square into fr square. That is something very much similar to last one also, but here actually this r and this r square, they are dependent on each other. So straight away saying that that will be constant is not a right thing. Earlier x and y, these two things were independent to each other. So these two becoming equal only if they are constant. But here I will use some other method which they have given here also. Let us call this as some gr. Okay, and this will become gr square. Now if we keep doing this thing, we will get this to be gr power 4 and so on. In the end it will be g of r power 2 power n if I do it n times. Okay, in fact if I write r power 2 power n as y, Okay, we can write this as reverse also. We can write this in the reverse order also. So here we will get g of y is equal to g of, I think, y power 1 upon 2 power n. You can see if r power 2 power n is y, then r will be actually equal to y power 1 upon 2 power n. Okay, now if I change n to infinity, if I change, if I bring this n towards infinity, you can see this 1 upon 2 power n will approach to 0. Okay, so for any function, this gy will be approaching to, because it's a continuous function, this will be approaching to g of, for any value of y, if power is approaching to 0, it will be approaching to 1 plus, actually 1 plus, because it will be 0 positive. Actually 1 plus or 1 negative, it will depend if y is greater than 1 or y is less than 1. Y is greater than 1, then this y raised to the power 0 plus will be 1 positive, it will be 1 negative if y is between 1 and 0. But because this is a continuous function, so both limits should be same only, and this gy should also be having the same value that it will have at x equal to or y equal to 1. So gy will be equal to g1, then only this function can be continuous with this condition. So here gy was actually y into fy, and that will be equal to g1, that is some constant, and you can choose to have any constant here. So here also we are getting the function as g of 1, that's a constant, upon y. So I think that is clear how this is done in some other method. Now coming to this question number 5, it says two distinct real number r and s are said to form a good pair if r cube plus s square is equal to s cube plus r square. Okay. Now what should be the property of these r and s? Let us see. And to do this, I'll write this as r cube minus r square is equal to s cube minus s square. So if we take a function fx is equal to x cube minus x square, which is given in the hint also. So we have to find whether we can find a portion of domain of this fx where it is many one, and two different values of x can give you same value of the function. So these different values of x will be forming a good pair. Okay. Now to understand this function, let us see how this is behaving. We can take x square common, so x minus 1 here, and you can see its roots are 0 and 1. After 1 it is positive, here it is negative, and x is equal to 0, it is having double roots. So the sign will not change. So here it will be roughly, diagram will be like this, and there will be a point of minima here. This 0 should be point of maxima. To confirm this, let us do the differentiation of it, and we get 3x square minus 2x. I can take x common, we get 3x minus 2, and you can check the sign of this will change, like 0 here and 2 by 3 here, plus, minus, and plus here. So you can see this 2 by 3 will be point of minima and 0 will be point of maxima, exactly as I have drawn this diagram already. So this point will have x coordinate to be 2 by 3. So let us do the further calculation in our next slide. Find a good pair a comma l with the largest possible value of l. Okay. So please see, in this diagram it is very clear that if we are looking for those values of function which are repeating, so that is actually repeating between these two lines. Let me draw a line which is parallel to x-axis. This is x-axis, and this is a line parallel to x-axis and tangent to 2 by 3. So between this region only you can see we are having the value of functions which are repeating at multiple points. But after this or before this, there is no value of function fx that is getting repeated. Okay, so any good pair, whatever we can get, it will be within this. So to get a good pair a comma l with the largest possible value of l, I think l has to be 1 here, because this is the largest number where we are getting value of function as 0. At 0 also the value of function is 0. So I think in first part this L is 1 and A will be 0. So this first pair A comma L will be actually 0 comma 1. Now similar to this point will be smallest point, and let us call the value at this point will be S. Okay. Now to find this value of S, what we can do, we may find the value function at 2 by 3, or without that also we can do it. Please see how. This line is actually corresponding to y is equal to f of 2 by 3. This S will also be having same value. S will also be giving us same value what we are getting at x is equal to 2 by 3. So here if I solve for this cubic, fx minus f of 2 by 3 is equal to 0, and fx is x cube minus x square minus f of 2 by 3. Here I will try to solve this question without finding f of 2 by 3. You can see this is a cubic whose one root is 2 by 3, and not only one root, actually this line y is equal to f of 2 by 3 is a tangent of this graph at 2 by 3. So 2 by 3 should be a repeated root, and other third root will be this s. So from sum of roots, which is this, is equal to 1, we get s to be equal to minus 1 by 3. So this point is actually corresponding to minus 1 by 3, and whatever value of function we get at minus 1 by 3, and you can verify that f of minus 1 by 3 and f of 2 by 3 will be same. So in this first part, this s will be minus 1 by 3 and b will be 2 by 3. So s comma b pair is actually equal to minus 1 by 3 comma 2 by 3. Now they are saying for every good pair c comma d other than the two we have found, show that there is a third real number e such that d comma e and c comma e are also good pairs. Please understand, as I told you, that any good pair can happen between these two lines only. This is y is equal to 0 line, and this is y is equal to f of 2 by 3. Okay, and if we leave these two pairs aside, 0 comma 1 and this minus 1 by 3 comma 2 by 3, then I think whatever point we are going to get, they will be lying strictly within this range minus 1 by 3 comma 2 by 3. I am talking about the interval bracket, not this bracket. Okay, so within minus 1 by 3 to not 2 by 3, I think it will be 1. Minus 1 by 3 comma 1 interval, we will be getting this kind of good pairs. So suppose I find two good pairs like C and D, and if they are good, they are forming a good pair, that means line joining C and D should be parallel to x-axis, so that value of y coordinate at these 2 points is same. But if I extend this line further, you can see not only at C and D, there will be another point, let us call that as E, where the value of function will be same. So if C comma D is a good pair, then C comma E will also be a good pair, and this D comma E will also be a good pair. So I think this completes this first part. Now coming to the second part, this is one very tricky part of this question as per my opinion. It says show that there are infinitely many good pairs of rational numbers. Both numbers are rational numbers. Please understand. First of all, what I said in our last slide, I'll repeat it, that our good pairs will be lying within these two lines. One is y is equal to f of 2 by 3 or minus 1 by 3, you can say. This point is minus 1 by 3 comma f of minus 1 by 3, and this y is equal to 0. Okay, now I can choose any value of x from minus 1 by 3 to 1, and definitely I can choose some x equal to r, that is rational number, because minus 1 by 3 to 1, there are infinite rational number. I don't think any further explanation is required for that. So you can have infinite rational number in between. But suppose this is r, which is rational number, and we draw a line that is parallel to x-axis, and we get corresponding to r this point as s and this point as t. So this rs or rt will form a good pair. But is there a guarantee that s and t will also be a rational number? That is the main thing. The main thing about this part of this question. Please understand. Suppose this line, I call this as y is equal to f of r. So as I did before also, let us write a cubic fx x cube minus x square minus f of r equal to 0. And f of r will be some rational number, because f of r here, let me write, f of r means r cube minus r square. R is rational, so r cube minus r square is also rational number. Rational number, let us call this as q. So we get this cubic, x cube minus x square minus q is equal to 0. Now, is there a guarantee that this will give you two rational roots? We can do the factorization and we get one factor x minus r for sure, because fr we are putting here, so x is equal to r should satisfy it, but other one will be giving us a quadratic, x square minus something plus some q upon r here. But if this quadratic can give us both the roots rational, then only we can say that for this r we got rational roots. But if this is giving us irrational root, then I think saying that we have got rational numbers, good pair, will be incorrect. Now, I'll tell you how I can do it. Actually, I'll try to prove that this is going to have rational roots. Okay, this can be done this way also. Please see, I will write this given relation here as s cube minus r cube. S cube minus r cube is equal to r square minus s square. I think s square minus r square. S square is equal to r square. And if you factorize it, you get s square plus r square plus s into r is equal to s plus r. Actually, r and s are different, so s minus r factor will be cancelled, and here we get a quadratic in s, which is s square plus I think r minus 1 into s, yes, and plus r square minus r is equal to 0. Let us check the calculation. S square plus r minus 1 into s plus r square minus r is equal to 0. Here r square minus r will be rational, r minus 1 is also rational. Okay, they both are rational. So that means to get rational root of this quadratic, we just need to make sure that discriminant of this is perfect square, which is r minus 1 square minus 4r square plus 4r. So this becomes actually minus 3r square plus 2r plus 1. Okay, and you can see we can do the factorization of this easily. I think one of the factor comes out to be 3r minus 1 and other is minus r plus 1. Let me check. Plus 3r, actually 3r plus 1 here and minus r plus 1 here. So minus 3r square plus 3r minus r plus 1. Yeah. So these are the two factors which we are getting. Okay. Now let us do this question in the next slide. So what we have got here, that D came out to be 3r plus 1 into minus r plus 1, and we want this discriminant to be perfect square of some rational number. A belongs to rational number. Okay. Now please try to understand, in order this to become perfect square, one of the choice could be that this 3r plus 1 becomes equal to perfect square times minus r plus 1, where b is also some rational number. What I'm saying, if 3r plus 1 becomes perfect square times minus r plus 1, then I think then this d will be actually equal to b into minus r plus 1 whole square. You can check. And this thing will be equal to a, because this b is rational number, minus r plus 1 is a rational number. Then we will be able to conclude that for that r, we got d to be perfect square. Now, if 3r plus 1 is equal to this thing, what will be the value of my r? I think the value of this r will be, if I bring this it here, we will be getting, I think 3 plus b square into r is equal to b square minus 1, yeah. So this r square will be equal to b square minus 1 upon b square plus 3. This is not r square, this is r. Okay, and this is a function, you can check its maximum value will be approaching to 1, minimum value will be minus 1 upon 3. It can be checked. So this r value is within this to this. In fact, this is the condition for this d becoming positive also, because this d will be positive only when this r is from minus, this minus 1 by 3 was here, minus 1 by 3 to this 1 point. Okay, now please let me know if you understand this or not. This b, if it's a rational number and I can choose infinite rational number, so that this r will be b square minus 1 upon b square plus 3, also a rational number. In fact, for all b being rational number, this will be a rational number. So if I take this kind of b and I put this value of r here, if I take this value of r here, then other value of s corresponding to this r, so I'll say for this r, we will get s also to be a rational number, and hence I think we are done, because b can be infinite values, and if b is infinite values, then this r will have infinite values for which we will get s also to be rational number, and hence we are done that there will be good pair of rational numbers. Now coming to the last question, one very interesting question. Solve the following. You may do 1 and 2 in either order. Let p is a prime number. Show that x square plus x minus 1 has at most 2 roots modulo p. That is the cardinality of n such that n between 1 to p and n square plus n minus 1 is divisible by p is less than or equal to 2. Find all prime numbers p for which this set has cardinality equal to 1. Okay, now let us do first question, first part. So I'll start with that saying n cannot be equal to p, because if you take n is equal to p, then it cannot be divisible by p. Okay, that means the strict inequation or better inequation on n should be this p minus 1, and this is greater than 1 here. Okay, and suppose there are 2 roots, a and b are 2 roots of this equation. That means p will divide a square plus a minus 1, and also p will divide b square plus b minus 1. That means p should divide their difference also, a square minus b square plus a minus b, which means p should divide a minus b into a plus b plus 1. Here a and b both are such that they are less than p minus 1, greater than or equal to 1. And if we are taking 2 different roots, so let us first talk about when they will be different roots, and then we will talk about same roots also. So if different roots, then this a minus b difference mod has to be less than, I think, p minus 2 will be the maximum value and 1 will be the minimum value. So this is not divisible by p. That means p should divide a plus b plus 1. But from this condition, once again, a plus b plus 1 will have maximum possible value to be p minus 1 plus p minus 2 plus 1. So I think 2p minus 2p minus 2, and greater than or equal to, I think here this will be 4 if a and b are different. 1 plus 1 plus 2, yeah, 4. Now a plus b plus 1 being divisible by p means it should be multiple of p, but it is less than 2p plus 2p minus 2, and p being prime number, so this a plus b plus 1 has to be equal to p. So for any root a, p minus a minus 1 is other root. So you cannot have 3 roots, because for suppose if 3 roots are there, if a, b, c are 3 roots, okay, then we can say from this relation for a and b, if they are root, then B will be P minus A minus 1, and if A and C are root, then C will also be P minus A minus 1. This gives us that B will be equal to C. So there is at most two roots. Okay. Now, when will be one root? Please understand, to prove there is when it will be one root, I'll claim first that if P divides A square plus A minus 1, then P will definitely divide P minus A minus 1 square plus P minus A minus 1 minus 1. This, though I have taken from previous slide where A was not equal to B, but without that condition also you can check by opening these brackets. You will find there are many terms that are multiple of P, and that remaining things P times integer into plus there will be remaining thing will be A square plus A minus 1. It can be checked. That means if P divides this, P has to divide this also. So automatically if A is one root, P minus A minus 1 is definitely a root. So if only one root means A has to be equal to P minus A minus 1. Okay, so what we get here, P has to be equal to 2A plus 1. Okay, if there is only one root, then prime number P has to be in terms of that root as 2A plus 1. And here all, in that case, this 2A plus 1 will divide A square plus A minus 1. But this 2A plus 1 also divides, 2A plus 1 whole square. Why I am writing this? Because if you use this relation once again, you can write this as 2A plus 1 divides 4A square plus 4A minus 4. That's a very, important trick in number system questions. Now, if you open this whole square, you get 4A square plus 4A plus 1. So, taking their difference, we get this divides 5. And P is this prime number 2A plus 1, which divides 5. So, I think P can be only one thing, that is 5, when A is equal to 2. So, for this case 2, for case, so this part of this 1, only P equal to 5 is the answer when cardinality is 1. When cardinality is 1, then P is equal to 5. Now, I will raise one question which I am going to use next, whether it is compulsory that we need to have one root or two root, or there is a possibility that we may have zero root also. Okay. So what I have concluded that we may have zero root also. I'll just show you that suppose I take P is equal to 7. Okay. And then I take N is equal to 1. This expression becomes equal to 1. If I take N is equal to 2, this expression becomes 5. If I take N is equal to 3, this becomes 9 plus 3, 12 plus 1, 11. If I take N is equal to 4, this becomes, I think here difference was 4, then 6, now it will be 8. If I take 5, it will be 29. If I take 6, difference will be, I think, 12, so this will be 41. If I take N is equal to 7, this becomes 55. Now you can check for P is equal to 7, which is a prime number. Among all values of N from 1 to 7, this expression N square plus N minus 1 is such that none of this is divisible by 7. It can be checked. So there is no guarantee that you are going to have at least one root. You will have either 0 or 1 and maximum 2 roots. That is all about this part. Now I'll come to this second part. Please see. To the second part, let me add a few more slides for this. For the second part, we are given find all positive integers n less than or equal to 121 such that n square plus n minus 1 is divisible by 121. First of all, my claim is that there can be at most 2 roots. There can be at most 2 roots. With the same logic, and this n cannot be 121. with the same logic. So n will be less than or equal to 120 and greater than or equal to 1 if a comma b are roots. Okay, so I'll do it fast now. A minus b and a plus b plus 1 should be divisible by 121. A, b being between 1 and 120, so this cannot be multiple of 120. So this a plus b plus 1 has to be 121. Again same logic, a plus b plus 1 will be within, maximum value will be 120 plus 120, that is 240 if they are different, and a and least value will be 4. So this is my value of a plus b plus 1. So a plus b plus 1 has to be 121 if a and b are roots. So there can be at most 2 roots only. So if one root is a, then other root would be 120 minus b. Now how we can find one of the root? Now to do that, I will not go it directly by 121 because it's a big number. We will go it with smaller number. So let us first find some number a such that 11 divides this a square plus a minus 1. Now it is very easy to see that a is equal to 3 is the solution. 3 into 4, 12 minus 1, 11. So is a solution. In fact, from our result that we derived in our first part, we can check a is equal to 11 minus 3 minus 1, 7 is other solution. And there will be only 2 solutions for this from 0 to 11 is other solution. Okay. Now please see, we found that a 11 divides 3 square plus 3 minus 1, and also 11 will divide if I add any multiple of 11 to 3. Eleven will divide this also, you can check. If you open it, all the terms will be multiple of 11 or remaining thing will be this thing. So what I am claiming, this thing that 3 plus 11k whole square plus 3 plus 11k minus 1 is always 11 times n. Okay, but there is a chance that this becomes multiple of 121 also, because if this number is multiple of 11 for some value of k, it could be multiple of 121 also. So to find, so let us find value, let us find k, so that this 3 plus 11k square plus 3 plus 11k minus 1 is equal to 121. Let us say some let me put L. Okay, so here already this 121k square term is multiple of 121. So remaining thing will be 11 into 3, 33 into 2, 66 plus 11, 77k plus 9, I think 11 will be remaining, is equal to 121L. That means this is already multiple of 121. So we want this to be multiple of 121, and that means 77k plus 11 is divisible by 121. That means 11 divides 7k plus 1. Okay, and you can see that 7k plus 1 divisible by 11, very simple observation gives that k is equal to 3, gives you 7k plus 1 is equal to 22, and hence for k is equal to 3, we get this number to be multiple of 11. Okay, and for k is equal to 3, my number n, this n is equal to 3 plus 11k will become 36, and for this 36 square plus 36 minus 1 is divisible by 11. It can be checked. It can be divisible by 11, and also not 11, sorry, it will be divisible by 121. And also, as I proved earlier, that if a is a root, 120 minus b will be root. Other root would be 120 minus 36, that is 84. And you can check that 84 square plus 84, that is 84 into 85 minus 1 is also divisible by 121. 121. So these are the two values of n which will satisfy it. Okay. Now coming to third part, which says what can you say about the number of roots of this modulo p square for an arbitrary prime, that is cardinality of this. So I will say in the third part the answer would be at most 2. If 1, then I'll just say that a plus b plus 1 will be equal to p square, and sorry, I will write this way: if at most 2, say a and b, then once again a plus b plus 1 will be equal to p square. If only 1, then this will be 2a plus 1 is equal to p square. Okay, and if any such number is possible, then it will be true, it will be possible for this only. So, and there is no guarantee that you will be having at least one root also, as I have shown you for 7. So for any prime number, it is not guaranteed that we will be having at least one root for this. So this completes the solution of this question. I think this was awesome question. I took more than maybe half an hour to explain this question, but this was really very good question, and I will say this paper was too good, and I will rate this as a difficult paper. Thank you so much. Bye everyone.